Tarun sir, let's start. Aditya miss, can you hear me?
Yes, miss.
Okay. Okay, all. Let's start. A very good evening to all the dignitaries, distinguished participants, faculty members, and organizers joining us for day 2 of the Adult Faculty Development Program. It's my pleasure to welcome you all to this evening session. We are delighted to see your enthusiastic participation yesterday, and we look forward to another insightful session today. We have two eminent speakers with us today, and we are sure their expertise will enrich our understanding of today's themes. It's a humble request. Before we begin, I request all to kindly turn your camera for some time so that we can take a group screenshot for documentation and memories. Thank you. And also, dear participants, kindly note, this is a kind reminder to you. Please submit the feedback forms for the two sessions separately of today's program. Your feedback is valuable and will help us improve the quality of future session. Also, both the feedback form is essential for recording and updating your attendance. Thank you. Let's move on to our first session. Our first speaker for the day is Dr. Parijat Pallab Jana. Dr. Jana is a distinguished senior scientist in the Material Science and Technology Division at CSIR NIST, Trivandrum. He holds a PhD and MTech in Metallurgical and Materials Engineering from the IIT Kharagpur. Throughout his illustrious career, Dr. Jana has contributed significantly to the field of material science with experience spanning from academic teaching at reputed institutions to impactful research in interdisciplinary material development. His research interests include high entropy alloys, metallic glasses, advanced utility alloys, and sustainable materials. He has an extensive publication record with over 15 research articles published in leading international journals such as Material Science and Engineering A, Materials Today Communications, and Thermochemica Acta. His work has been recognized at numerous national and international conferences where he has delivered invited talks, keynote addresses, and presented research posters. Dr. Jena has attended over 20 conferences and symposia showcasing his active engagement with the global scientific community. Dr. Jena's innovative research and dedication to advancing material science have earned him a reputation as a leading scientist in his field. His contributions to continue to influence the development of sustainable and high performance materials for various industrial applications. We are truly privileged to have you with us today, sir. I warmly invite Dr. Parijat Pallab to deliver the first session. Sir, the virtual stage is yours. Please, sir.
Thank you. Thank you very much. Good evening, all. I hope my voice is audible.
Yes, sir. Very clear.
Okay. Thank you. Thank you very much, madam, for your kind introduction. And a very good evening to all the participants. So today we will spend around one and a half hours, and I will just not deep dive into the science, but I will briefly explain how the advanced materials is changing our society from each day to day. So without further delay, let me share my screen. I hope my screen is visible.
Visible, sir.
Okay, thank you once again, and good evening to each one of you. So the today's topic of discussion, we will briefly discuss about advanced alloys and composite. Although this topic requires a actually semester's coursework to complete that thing, but we will try to cover as much as possible with this in 1.5 hours. And after this session, if you have any questions or if you have any queries, you can ask. I will try to answer those questions and queries. So if you see the selection of materials in our society and selection of materials, so the materials mainly divided into two parts. One is metals and non-metals. In metals, we have ferrous, that means which contains iron, and another is non-ferrous, which does not contain iron. In ferrous, we have cast iron and steel. Cast iron means the it's a combination of iron and carbon, and the carbon percentage is higher. In case of steel, the carbon percentage is restricted to 2.18%. In case of non-ferrous alloy, we have lightweight alloys like aluminum alloys, magnesium alloy, titanium alloys, super alloy like nickel-based alloy, cobalt-based alloys, and other alloy also, copper, gold, tin, lot of alloys are there. In non-metals, we have ceramics and polymers. So is this category, is this specification plays a significant role in our day-to-day lives, in our society, in our living standard, in our whole country as a development, or whole world or whole universe as a development. This type of materials plays a significant role. So before going to the advanced materials or what are the advancement is happening in today's world, let me take you into the history. So I know how many of you have heard this term Damascus sword, wood steel. Today, India is producing around 150 million ton of steel. Still, we are importing steel from China, Korea, Japan, around 10 million tons. But there was a time in ancient India, that time India was a largest steel producer, and not only the producing the steel, we used to export the high quality steel to the Middle East, Europe, European countries. If you can see the map on the right hand side, the Indian map, these are the sites, the ancient site where this kind of steel making tradition or steel making procedure was there. So this wood steel is a particular kind of steel which is having iron with a carbon percentage ranging in between 1.5 to 2.8%. And you might know that the wood steel, actually the name is a British name, but the actual word is came from ukku. In Kannada and Telugu it's ukku, and in Tamil word urukku. Okay, so this is actually European or British version of ukku. They are difficult to pronounce this ukku, so that we make it wood steel. Okay, so this particular steel has a very significant properties which is very strong, flexible, and super sharp. So with this steel, that time ancient India, they used to make a sword which is known as Damascus sword. Okay. So that was so sharp and so strong that nowhere in that at that type of world nobody known the how to produce this kind of steel, and India was so advanced in this making of this steel. They used to export this steel to the Middle East and Europe. Okay, so we should take privilege and we should take pride in our ancient Indian development, that this kind of steel making procedure or the advanced material procedure was known to only Indian, that the continent which is known, which is mapped in the Indian map, but not known to the other parts of the world. Okay. Still, this kind of sample or metal is being stored in archaeological Society of India archaeological site. You can people are doing a lot of research how this thing, because nowadays if you want to make this kind of steel, it is very difficult to reproduce this kind of steel. Okay. So our ancient generation or ancient India, they might have used some techniques or some procedure which is still unknown to our current civilization. So a lot of extensive research is going on to dig out that what make this kind of steel is so strong, so sharp and flexible. So this is a one kind of example. So and we can tell that this is a advanced material of our ancient world, which is only known to our Indian civilization, not to other part. Now, coming to the second example, the second example is super alloys. You might have heard this term super alloys. The whole world of aviation is you cannot think of aviation industry without these super alloys. It's a special class of advanced alloys. I will not go dive into the what is the characteristics, everything. I will just briefly tell you what is this thing. So this is a particular type of alloys which is being engineered to perform at high temperature and high stress. You might know that the jet engine which is being used to propel our aircraft, civil aircraft, fighter aircraft, or defense aircraft, all the aircraft industry is based on this jet engine. And the jet engine has a part that are being made using this super alloy. So the super alloy is a metallic alloy which has been designed to withstand the temperature which is the 0.7 of its melting temperature. And the super alloy can be a iron-based super alloy, cobalt-based super alloy, and nickel-based super alloy. Okay. So the predominantly used super alloy is the nickel-based super alloy. And you can see the melting temperature of nickel is 1450 degrees centigrade. But if you use a nickel-based super alloy, the operating temperature will be 1000 degree around. And the examples are also given in the slides also. So what happened? This material, why it is so important? Because the material is prone to not only work at a high temperature, but you think that when a jet engine runs, it can experience a temperature of 1000 or 1100 degrees centigrade. That is too high for a material to withstand its strain. Not only that thing, when the aircraft flies above 34,000 feet or 36,000 feet, the outside temperature is -40. So you can think of that a material which is experiencing 1200 degrees centigrade inside and the outside temperature is -40. You think of the temperature gradient, -40 to 1200 degrees centigrade. So a material has to withstand that temperature gradient. Generally, in general speaking, if you put any material or something in liquid nitrogen, if you put, it will become very brittle. It will lose its strain ductility. It will become very brittle. But this special class of material has to withstand all this temperature rigor, and it has to withstand and they have to perform and run the jet engine so that the aircraft or the civil aircraft or military aircraft flies. So the nickel-based super alloy, you can see in the right-hand side the figure. You can see this is a kind of turbine blades. So the turbine blades are peripherally inserted into the jet engine, and this is a typical design of a turbine blades. And this turbine blades is made up of a nickel-based super alloy, generally Inconel 718 super alloy. So if you see this super alloy in a optical microstructure or scanning electron microscope, you can see it consists of this kind of a matrix and this precipitate phase. So for this kind of super alloy, it is made up of aluminium, nickel, and this particular matrix and the particular precipitate phase forms, which give rise to this kind of strain. Okay. Now you see this the strength of this superalloy as a function of temperature. You see yield strength. Yield strength is in the y-axis. I have shown the yield strength, and x-axis is the temperature. If you see the inconel, this is a nickel-based superalloy. If you see the operating temperature, it can retain its strength up to around 700 degrees centigrade, 700 degrees centigrade without any protective coating and other things. Inconel, if you use, it can go up to 700 degrees centigrade. Okay. Now this A286 is a iron-based alloy. It's a stainless steel A286. You can see its variation. Then titanium alloy is also the titanium, 6 aluminum, 4 vanadium. That is also, you can see the strength. Aluminum alloy is there. Then 304 stainless steel is there. L605 alloy is there. So you can see that apart from, if you compare this alloy with the other its counterpart, the nickel-based superalloy is showing superior strength, not only at room temperature, but it retains its strength as a function of temperature up to 700, 800 centigrade. But if you still give a protective coating or engineer cooling channels, everything, you can still further use up to 1000 degrees centigrade. Now you see this is a simple experiment how it looks like. So this is a four cylindrical bar, you can tell, cylindrical bar, which is made up of a standard 304 stainless steel. We know what is stainless steel. Every day we use our stainless steel utensil, other things. So this is made up of a stainless steel, 304 stainless steel, and this is a standard titanium alloy. Second case. Third case is a superalloy. It's an iron-based superalloy, A286 iron-based superalloy. And fourth case is a nickel-based superalloy, which is Inconel. The commercial name is Incolet 718. Okay. Now this 4 bar has been experiencing a we put a sufficient load of around 100 kg so that each bar experience a stress, internal stress of 300 megapascal. Okay. So each bar is experiencing 300 megapascal. At the same time, we are increasing the temperature up to 600 degrees centigrade. Now, if you run this experiment, you see that the standard stainless steel alloy will fail, will break apart at around 10 hours. And the titanium 6 aluminum 4 vanadium alloy, that means 6% aluminum, 4% vanadium, that will fail around in 30 hours. And if you take a superalloy, iron-based superalloy, when it comes to superalloy, the time to failure is 3.5 years. It will take if you put this constant 600 degree temperature and constant load, it will take 3.5 years to this load will fracture, which is a phenomena we know, which is known as creep. We will not go into details, but you see the superiority of superalloys as compared to the other conventional titanium alloys or stainless steel or iron alloy or aluminum alloys you can think of. But if you go to the nickel-based superalloy, you can see the time to failure is 8 years. So by this simple experiment, you can find out that how superior this superalloy is and what is these characteristics. The simple alloy which has been engineered, nickel, aluminum, we mix the alloying element in such a way that, such an engineering way that we need this kind of precipitate will form, and this precipitate will have the high temperature stability, and this material or this alloy will withstand the temperature. Okay, so this figure, if you see, this is a nickel-based superalloy block. Now, if you take a small block and polish it, and you see in the microscope, you can see this kind of grains. These are the grains, and the black lines are the grain boundaries. You can see a grain and grain boundary. If you still further zoom in using a scanning electron microscope or optical microscope, you can see some inside that grains. There is some black precipitates. Black things are there. Okay. So what is this? So this alloy, generally all superalloy are strengthened by precipitation strengthening. So precipitation strengthening means, so if you see this figure, we have a matrix. In the matrix, some small precipitates are there. So what happens when it is in temperature? If in a huge temperature, if you use that material, So when the metal try to deform by a movement of dislocation or movement of any defect, the small precipitate will act as a barrier to the dislocation. So it will not allow the dislocation or defect to move further. It will restrict the movement, and that's why it give rise to the high temperature strength or the superior strength of nickel-based superalloy is having. Okay, so this is very much important, because how much precipitate do you want, what is the size, what is the type, all these things as a metallurgical engineer or a materials engineer, we have to we have to tune that size, morphology, all these things to give rise a better property. And if you take this small square box, if you take further and you take this small square box and see in a transmission microscope or some advanced microscopic technique, you can see that these are the nickel, chromium, molybdenum, iron atoms are arranged like this, So from atomistic scale to a bulk macro scale, these are the property or these are the sequence of events that are happening and that are give rise to this excellent strength at higher temperature of this nickel-based superalloy. So the nickel-based superalloy mainly we have 50 to 60% is nickel, then some 10% maybe cobalt, then molybdenum, iron, and some other refractory like niobium, molybdenum. We add that thing. So the purpose of nickel is the nickel give a FCC crystal structure, phase center cubic crystal structure. The atoms are arranged in a FCC unit cell, and it gives a excellent stability at high temperature. It gives a solid solution strengthening with the other element like cobalt and iron. Then molybdenum or niobium, this is give a high temperature, because these are a material whose melting temperature is very high. That give rise to the high temperature properties, and obviously the precipitation hardening. And the chromium also we given chromium. We added chromium. So chromium 8 to 10% chromium has been added. So it will give a corrosion resistant coating, because if you add chromium will abruptly on the surface it will form chromium oxide. It's a self-filling oxide layer it will form, and that oxide basically protects the material inside like nickel or molybdenum and other things. So this nickel or the nickel-based superalloy is strengthened by the precipitation strengthening. By the precipitation can be of two types. One is we call gamma prime, another is the gamma double prime. The gamma prime is the Ni3Alti, and the gamma prime is Ni3Nb. So these are the two type of precipitates which give rise to this kind of strength. Now, if you see the historical development of these alloys, so generally the idea came that people try to use a alloy or material which can withstand more and more temperature. From that idea it came. So initially people have developed some steel composition, which can withstand high temperature. Then they made an alloy, nickel and cobalt based alloy in 1930. And after 1930, there is a first generation of superalloy has been developed around 1930, when specifically the military use, when they need a material which can withstand high temperature. And after 1950, with the further improvement in the processing techniques, vacuum technique, and other melting casting techniques, people still refine the superalloy composition, and the superalloy has been widely used after the 1950 with superior strength. You can see the image of the first maiden flight of Boeing 707 in 1957, which is powered by the jet engine. Okay. And this is a Rolls-Royce Conway turbojets. Before 1960, we used to have a propeller flights. We might have seen some propeller flights. Still, it is in some ATAL flights are there. But it is the year 1957, December 20, the first flight which is having turbojet engine with nickel-based superalloy put as a turbine blades in the engine. Okay. The first passenger flight was done at 1958. Okay. So this is the historical development, and from 1957-58 to the 2025, lot of improvement in property, lot of capacity, lot of things has been developed. Okay, it's a incremental development every day. People are doing, industry are doing, R&D institutes are doing to give service to more and more wider aspect. Now the other after superalloy, there is another engineering marvel we call it shape memory alloy. Shape memory alloy. Shape memory have been used as stent, cardiovascular stent. So what is that alloy? Particular alloy is a alloy or is a functional alloy which is a unique property. It can remember its shapes. Remember its shapes. So the basic mechanism I will tell you. But yearly in India, you must have know that around 5 to 6 lakh cardiovascular or angioplastic operation is going on. And if you have a blockage in heart, they operate and they put a stent, metallic stent, which is made up of a nickel and titanium, 50% nickel, 50% titanium. So this simple nickel and titanium alloy, how it give rise to some shape memory effect, and that can save the uh, plenty of lives in today's world. That I will tell you. Suppose if you have a heart blockage, that means what your the blood flow will be restricted, and you can have a heart attack and arrest everything. But if you are if you have diagnosed with this disease, so they will do a operation and put a metallic stent, which is made up of nickel titanium. So you can see that initially the shape is like that. So when this stent attain the body temperature, it will automatically expand. Automatically expand. You can see the second figure, expand, and through this thing, the blood circulation or the blood circulation or blood flow will be easy, and you can avoid these things. It is used in everyday life in our medical sciences. So what happens? I will tell you the basic mechanism. It's a simple thing. So you have a tube or a rod of a material. Just you bend the material. That means bending means you bend the material. That means you are deforming the material. So after deforming, you take this deformed material and just simply put the heat. If you heat it, it will automatically take its original shape. It will take original shape. Then you can cool down. It can return its shape. So this is the basic fundamental is happening in case of shape memory alloy. Now, if you try to understand in terms of stress and stress behavior, so we first we have a twinned martensite. It's a phase twinned martensite. We can say twinned martensite phase. So if you deform the material, that means you are giving deformation, you are giving stress, the material is getting deformed, and after deforming, the deformation is being accommodated inside the twin martensite, and the material become detwin martensite. Okay, the material has been deformed. After deformation, you just release the load, So it will be written its shape like that. Then you heat it. After you heat it, it will become detwin martensite to austenite, and from austenite, if you cool it, it will become twin martensite. So this is a cycle of event is happening in a same memory alloy. That means the material can retain this step, and that development has been used in our practical application. The another example is that radial stiffener for rover. If you see that we send rover to Mars, or rover to the for industrial exploration, we steep the rover. So we cannot put like a tire or rubber material, which is the made which is the main constant of a wheel. Apart from that, they put some radial stiffener which made up of a nickel titanium alloy or copper aluminum manganese alloy. So these are the two type of alloy which shows the shape memory effect. Not all other alloy doesn't show, because this is a particular characteristics of a material of an alloy which shows this kind of shape memory behavior. That means they retain the shape. So the rubber wheel also can be made up of a shape memory alloy. So because you don't know the surface morphology of a moon or Mars, There may be some hill part, or there may be some ups and down road morphology we don't know. So what happens if the wheel can remember its shape, although it experienced some obstacle during its path, it automatically can retain its shape. So that is the beauty of this kind of alloy, and it is being still further. And this whatever I am telling, this is not in the develop or not the development has stopped. If every day people try to enhance enhance the property. Suppose in case of super alloy, now the super alloy can be used up to 1000 or 1200 centigrade. Now people try to increase the temperature range to 1500 degrees centigrade or 1600 centigrade. So by increasing the temperature, you are increasing the efficiency of engine. Efficiency of the engine means, suppose one aeroplane which can carry above 400 passenger, if you increase the efficiency, it may carry 800 passenger. So every day you are trying to increase the efficiency by development in this advanced materials or advanced alloys. The another class is aluminum alloys. Everybody knows the aluminum alloy. You might know that this before 1900 maybe around 1800 or 1850. That time aluminum was 17th century or 18th century. Aluminum was more precious than gold, because the aluminum, which is more to extract the aluminum, which is very difficult, because we extract the metal like iron, all metal I was talking about, like nickel, iron, aluminum or copper. They don't exist in nature as a pure element. They exist in the form of oxides, sulfide, chloride. They exist in the nature. So through extraction we have to refine this oxide into pure elements. So for iron, now you know that we have a iron making plant, steel making plant, iron making. So we took the iron oxides, then do a reduction process, and from iron oxide we make a pure iron. Similarly, for aluminum oxide, we have to make a aluminum oxide to aluminum, pure aluminum. But the reduction efficiency of aluminum oxide is very difficult, because aluminum oxide is very stable oxide. If you want to reduce aluminum oxide, you need very high energy consumption, and very complicated process. That's why the production of aluminum was very costly and very crucial and very very process intensive. That's why during 17th or 18th century, the price of aluminum was higher than the price of gold and the other elements. But you see, then in 1906, Alfred Will, one scientist, German metallurgy, German scientist. So he made a particular alloy. The alloy name is commercial name now today is also available, which is called duralumin alloy. So he took some aluminium, then around 4%, 3.5 to 5% copper, then some magnesium and manganese. Okay. He made an alloy and mixed it, melted and cast it, made an alloy, and he given this alloy to his student for measuring the hardness. So, but the student, what he did, so it was a Friday. So he instead of taking the harness on Friday, he will take the Saturday, Sunday is holiday. I will come on Monday. I will take the harness. Okay. So when Monday he came and take the harness, he got that the harness value has increased 3 to 4 times. Okay. So they might have thought that they must have done some mistake or something. So they repeat that thing, same thing they repeat. And they found that, yes, it is a common phenomena which is happening in this particular aluminum alloys, which is called age hardening. If you take a aluminum alloy, keep it in the simply you leave it for in atmosphere, it will automatically age harden itself. And this is the first paper it was published by Alfred. You can see that from time in 0 hour it is around 70, hardness even 70. But if you increase the time as a function of time, how the hardness has been increased. Simple, you don't do anything, you cast a alloy and keep it. With time, the material become hardened. Okay. That's a precipitation hardening. So after this phenomena, because earlier aluminum, you know, is very ductile, soft, it doesn't have a very strength. So it does not have any very commercial or very practical application. But when Alfred will first discovered this effect, and he found out that yes, aluminum alloy also can be hardened. It is not only ductile; it can strengthen the material. And the strength can be sufficiently high so that we can use that material in our practical uses of daily lives. So after that, you see the whole the aircraft body structure, aircraft fuselage structure, all these are made up of aluminum alloy because it's lightweight and simultaneously it gives rise to a high strength. So we will have a high specific strength in that kind of aluminum alloy. The another development which is this not recently, maybe after 1990 or in around 2000, this kind of happened. So till now, whatever example I given like super alloy, aluminum alloys or shape memory alloy, they are the percentage of the major alloying element, whether it is a iron, nickel, titanium, the percentage of major or aluminum, the percentage of major aluminum around 60 to 70%. But these two scientists, one is Brian Cantor and JWA. So they thought of that thing instead of adding the element like a 50 to 60%. If you add multiple element but equal portion. So the first they try to make a 20 component element. You can see the components is given 20 component, each having a weight percentage of 555. So 20 into 500. So you can see this is a 20 alloy composition they try to make. So from this try to make, but this due to some material solubility and the mismatch, they didn't able to succeed that thing. But what understanding or what knowledge they gather from this experiment is that if you take a 5 element or 6 element, if you take in equal portion like 20% or 25%, you can develop a new class of alloy which was not known to the humankind, which is called high entropy alloy. So what will happen if you add this element in equal portion, so it will give rise to the configurational entropy of the material. The configurational entropy will become so high that it will stabilize the simple phase like BCC phase and FCC phase or HCP phase, and simultaneously it will give rise to very high strength, high ductility. So you can tune a lot of property. So this is a development apart from the conventional alloy, some new class of alloy we call it has been developed, and this is still people are finding a lot of application of this kind of alloy where it can be used. I am not going into the details of this. It's thermodynamics and kinetics parts, just to give rise you the give you the explanation of that how the material is being discovered, so that you can appreciate its property and its application in our society. Now you see, as per the definition, it's a at least 5 principal element. At least you have to 5 so that the mixing entropy will be sufficiently high that it will stabilize the simple solid solution phases. And if you see that its fracture toughness and the strength and the function of temperature is as compared to the super alloy and other alloy in the material, you see the high entropy alloy is a fracture toughness, you see, is very high. So here we stainless steel, nickel alloy, polymer, metallic glass, all these things are the high entropy alloy sheets at the top. Similarly, if you stay in the as a function of temperature, they also shows a very high strength retention as a function of temperature. Okay. Okay, till now, whatever we have discussed is like a crystalline material or polycrystalline material. That means the atoms are arranged either in BCC crystal like that, or FCC crystal like that, or ACB crystal like that. It will be arranged. Simple, if you take a simple crystalline polycrystalline material. Now, what will happen if the atoms are not arranged in this particular arrangements? So from there, the discovery of non-crystalline materials or the amorphous materials actually starts. So I will just briefly explain how it has started the class. So whether you take an example of steel, nickel-based superalloy, titanium alloys, shape memory alloys, these are polycrystalline metal. That means the atoms are arranged in a particular way, in a unit cell. Okay. But in around 1960, Professor Paul E. Dues in Germany, Paul E. Dues, so he tried to conduct a simple experiment. Paul E. Dues, so whom he called as a father of supercooling. So his job used to, when we melt a material, it become liquid. So his job is to just undercool or rapidly cool that liquid into solid form. So that kind of experiment he used to conduct, and he used to calculate the degree of undercooling, degree of supercooling, and how the structure will be changing. So one day he was carrying out an experiment with an alloy which is a 75% gold and 25% silicon alloy. So he mixed 75% gold and 25% silicon. And what he did, he melted, make a liquid. Then he tried to make a drop of the liquid, and when the liquid drops falls, he tried to splat the liquid drop. Like liquid drop is falling, immediately it will splat the liquid drop. So by doing so, what he was doing essentially is very rapidly cooling that liquid. And when you can see the actual experiment setup, and when he saw that material in X-ray diffraction, X-ray diffraction, if you have a polycrystalline metal, it will show a peak. It will show a peak like that. If you it will show a peak as a function of the, it will show a peak like that. It will show a peak like that. It will show a peak like that. But what he found that, so after doing this experiment, he didn't found any peak. Rather, he found a broad diffraction maximum. So with this single XRD plot, he published one paper in Nature in 1960. So that was the discovery of a metallic glass. So that means by rapidly cooling a liquid metal, which is a combination of gold and silicon, you are destroying its crystal structure, and you are getting a structure. You're getting a structure where the atoms are randomly arranged. You can see the atoms are randomly arranged. In this case, the atoms are arranged in a particular crystalline in a particular way. You see, this is the way the atoms are in a particular fashion, in a particular direction. We call it a plane or helical direction. You can do that thing. For this is for a crystalline material. For polycrystalline material also, you can see this is for one grade the atoms are arranged like this. In another grade the atoms are arranged like this. So the atoms are arranged in a particular fashion in case of crystalline and polycrystalline materials. Okay, but in case of a amorphous material or glass, you see the atoms they don't have any particular order of arrangements. Okay, they are randomly oriented. So when Paul Dewey is doing experiment, ideally the gold and 70% 5% gold and 25% silicon should form a crystal metal like this, where the gold and silicon atoms will arrange in a particular way like this. But by doing this flat quenching, you was so rapidly cooled that alloy, the crystal structure got destroyed, or it is overcome the crystal structure, and the atoms become freezed in the liquid state. In liquid state, the atoms are randomly arranged. Okay. So this is a given an example of metallic glass, but there is some other glass. We know that Gorilla Glass. Everybody using phone, and everybody has a screen saver or screen protector, which is called as a Gorilla Glass or toughened glass. Okay. So this glass, everybody know our window glass. Whatever window glass we have, these are very brittle. If you just heat it, it will shatter into pieces. Okay. Although it has very high strength, but the ductility is very less. It is brittle in nature. You won't find any ductility. Like the alloys or steel has a ductility. You can bend the steel. You can deform to steel different shapes, different geometry as per our requirement. But glass, you can is very, if a glass is there, you try to deform it, try to bend it, it will shatter into pieces. Okay, it's very brittle. But still, you can further improve the strength and toughness of a glass, but some using some technique, and from there, the invention of the Gorilla Glass came actually. And this kind of toughened glass first is being used in the first series of iPhone when the iPhone has been launched. So this kind of a glass has been used, and it was made by the Corning Glass Company in the USA. So what they did, they have used a technique which is called a ion exchange technique. So I'll just um, briefly tell you what is this toughened glass is there. So this we are daily are using, but we don't know the mechanism of how it is happening. So that this is called chemically toughened glass. So you make a glass, you know it is a brittle. Then you take this glass and deep into a potassium nitrate solution. Okay, potassium nitrate solution. And glass is made up of a sodium oxide, silicon oxide. It's a mixture of aluminum oxide. It's an oxide glass. All our window glass is made up of a silicon oxide. It's a combination of silicon oxide, sodium oxide, aluminum oxide. If you melt and cool it, it will form a glass. So this glass contains a sodium atoms, and you dip this glass into a potassium nitrate solution. So what will happen? The moment you dip the glass into a potassium nitrate solution, some ion exchange will take place. So after some predefined given time, so what will happen? From solution, the potassium ion will diffuse into the glass, and from the glass, sodium ion will diffuse in the solution. So the ion exchange will take place. And as you know, the potassium atom having a higher atomic radius, then the sodium atom, once the sodium atom will diffuse into the glass, it will strengthen the glass because you have a limited space. You can think of a room. If you think of a room, in that room, suppose you are putting more and more people. So after a certain time, it will become so tight, so packed. So that we call it a stressed glass, so packed so that nobody is moving like that. So the potassium atom having a higher atom size, it will diffuse into the glass and it will become so tight, so freeze and so stressed that you need additional amount of strength to deform that thing. So you have a glass earlier before exchange, which is you can easily you may break, or if you just give a knock, it will break. But after exchange, you need to have you need to sufficiently apply the load to break the glass. So this way you can toughen the glass. This is another example, and this today's all mobile cover or any screen cover people are using this toughened glass. We call it sometimes call it a gorilla glass. This is a mechanism how these are being made, the glass. Okay, so the glass, as I told you, the glass formation. You take any liquid, any metallic liquid, any liquid. If you slowly cool, you take a liquid. So this is at a temperature high. This is all our liquid is there. So if you slowly cool, the line will follow like this, and it will form a crystalline. Will form a crystalline metal and crystalline glass. But instead of slowly cooling, if you rapidly cool enough, so instead of going this line, what will happen? Our curve will follow this line. If you plot a molar volume or a enthalpy or P energy, if you plot like that, it will follow like this curve, and after certain time, it will form a glass. Okay, it will form a glass. So what is happening? So you know that in liquid, the atoms are arranged in a random way. Liquid doesn't have any crystal structure. Like our solid material, solid alloy, they have a crystal structure, FCC, BCC, or ACP, as I mentioned. But liquid does not have any crystal structure. The atoms are randomly moving inside liquid. But when you cool this liquid very rapidly, so that means you are not giving sufficient time to move the atom so that it can take the initial position. Rather, you are doing it very fast that the liquid atoms are freeze in its place. And after a certain time, when the viscosity reaches around 10 to the 12 Pascal second, it will become a solid and it will become a glass. Whether the atoms are freezed in their position, they didn't give sufficient time to move so that they form a crystal structure. So that is the things happening in a in a rapid solidification or glass formation. So and if you put the right hand side figure, if you put that thing, how you know that or glass has been formed, you put that thing sample in a differential scanning calorimeter, and you can see this is a glass transition region, this is a crystallization region, and then followed by a melting region. You can get that thing. This is a glass transition endothermic event. This is a crystallization is a exothermic event, and also the melting is also an endothermic event. So you can track that thing, and we can scientifically pinpoint at what temperature what is happening, and what temperature melting happening, what temperature glass transition happening. So this is very important. Glass transition temperature is very important. I will give you some example where it is being used also. So this is about the concept of glass formation. So remember this thing when you try to form a amorphous or glass which where the atoms are randomly oriented, you need to cool the liquid very fast. You need to cool the liquid very fast so that atom does not get time to arrange themselves in a unit cell configuration. Okay. Now, I would like to make a point here also. So, how do you define a solid and liquid? The definition of solid, you remember the definition of solid is determined by the, if anybody asks you that what is solid, remember that solid has been defined by its viscosity value. If a material is having viscosity greater than 10 to the power 12 Pascal second, then we call it a solid. Okay. If a viscosity less than that thing, then we can call it a liquid. So viscosity, suppose how we tell that honey is more viscous than oil, and oil is more viscous than water. Okay. So like that, if you freeze the honey, it will viscosity will reach to a solid, and it will reach so high that it will not behave as a liquid. It will not flow as a liquid. It will become a solid. So this solid or liquid or the supercooled liquid or some in between state is defined by the viscosity range, which is very important for a glass formation point of view. So remember, solid is defined by the viscosity. If viscosity is high enough, that is 10 to 12 Pascal second, we call it a solid. Okay. So this is how the temperature has been, the glass temperature has been mm, derived using differential scanning calorimeter. So if you put a sample, you heat it, the endothermic heat flow, and you take a, this is a glass region. So and you take this, you will get this curve from the machine. You do a first derivative of the curve, second derivative of the curve. So you know the point at which the second derivative is 0 and the first derivative is maximum. That is the inflection point. From our simple mathematics, you can know inflection point. And from the inflection point, first you have to define a left limit range and the right limit range, and this is our inflection point. And you just draw a tangent from this point to this point, from this point to this point. And if you draw a tangent like this and draw a tangent like this, the midpoint we will call the glass transition temperature or onset of glass transition temperature. Similarly, if you draw a tangent like this and draw a tangent like from the right point, the mixed point we call a end, TG end point. So remember this thing, this is a glass transition is an event. So it start at temperature, in a temperature, in a sequence event. So you need to define the temperature very carefully for a material. Okay, as I was mentioning that thing, why the glass, the viscosity is important. This is how the viscosity actually viscosity changes. It's a logarithmic scale log viscosity as a function of temperature. So this is our melting temperature. This is the viscosity of liquid. You see, viscosity of liquid very low. So as you keep on cooling, the viscosity keep on increasing like this. Viscosity keep on increasing like this. So in between this viscosity as a function of temperature, we got different points like working point, softening point, deformation point, PG glaciation point, annealing point, strain point, all these things. And this point is very useful for a glass maker. Glass maker who do some different kind of shape in the glass, who do glass making. I don't know whether if you have seen any glass making process or things. So you should to know that all these things comes with experience when a glass blower or glass maker do this kind of shapes, different kind of a intricate shapes using glass, melting glass, how they make beautiful architecture, beautiful design. So he or she needs to know about all these points for a particular glass composition, and that particular point actually depends on the viscosity of the glass. Okay, as I mentioning, if anybody have visited the Salarjung Museum in Hyderabad, there is a dedicated floor is for that glass museum. You can see they have collected the glass from different parts of world, and they have stored this thing. Not only from the advanced glass, the ancient glass also. So you can see that different kind of architecture glass, your glass lamp to glass glass for glass utensils, all these things for aesthetics, architecture, looks, and these are not simply made. You need to know about their processing point, and it is very tough job to make. That's why very few glass blowers or experienced glass blower are there who can make this kind of intricate shapes and intricate design. There are a lot of varieties there. If you ever go to Hyderabad, you visit to this museum, you will find there is a plenty of items that are being made and kept there, and you feel amazed if you see that how the ancient people or the people used to develop this kind of material in the our glass making. Okay, so glass, how you will define that thing? So if you take a metallic glass, you put in extra diffraction. I told you instead of sharp peak, you will get a broad diffraction maximum. And if you put see in electron microscopy, you will see there is a featureless matrix. And if you take a selected area diffraction pattern, you will get a broad diffuse halo like this. Okay, that's how you define that. Yes, this metal is a glass. The another important thing of glass is that Prince Rupert drops. So from this glass, that concept of the bulletproof glass games. I will tell you how this bulletproof glass for a very VVIP VVIP person or a president or prime minister of a country, they need some bulletproof glass protection. How this has been developed, that will also give you a glimpse. This idea came from a Prince Rupert's drop. Prince Rupert's drop. So what they did actually during glass making, somehow they found that while they are doing on glass making process, one small drop fell into a water during quenching. Small drop fell into water, and subsequently it get cooled. But when the moment it falls into a water, cold water, you can see the outer periphery immediately which are in contact with the water will get suddenly cooled, but the remaining portion, the inside portion is still in molten condition or hot condition. So this kind of thermal gradient give rise to a very non-uniform stress distribution inside this kind of a drop. Okay, so this stress distribution, if you see in a polarized microscope, you can see this kind of a contour you can get where the outer part is very cooled fast, and the middle part is getting cooled rapidly. So I'll just quickly show you quickly show you one video how it is being made so that you can appreciate that thing. This is so high strength that it can fragment a bullet. You can see this video. I hope you can see my screen. My screen is visible. Can anybody confirm?
Visible, sir.
Visible, yes. So I'll just rightly. So they made the original document of this pin super drops. It is there in a library of a Cambridge. The original manuscript written by the scientist, and he found something and he given as a token to Prince Rupert that time. So that has been named after Prince Rupert drops. So this is the drop, and you see the video. People have done this thing, and video I will show you how they fired a bullet and how it is become. initially it will not, it will break, it will fracture. Glass, you know, once the crack started, it doesn't have any micro to arrest the crack. So once crack start, it easily propagate. That is the drawback of glass. But if you see the initial impact with the bullet with the glass, you see you see that time the bullet got fragmented. This is so high strength. But the crack started from the lower end, from this the bottom end, the crack started and propagated and it shattered the glass. But at the time it is remain intact, but the bullet got fragmented. So you can think of the strength of this one. Now how the crack from bottom is propagated. So that is the drawback of glass, is that once crack propagated, it is very fast the crack propagates. It does not have any microstructure obstacle to restrict the crack propagation. Okay, so this is the idea of the bulletproof glass concept came. So this is a typical glass composition, as I mentioned, glass composition. So I'll just quickly tell you that how this glass composition are being made. Bulletproof glass. This glass. This is we have two layers. One is a glass layer and another inter layer, which is a. I'm telling you about the bulletproof glass, which is transparent. So you have to, when a bulletproof glass is being, three things you have to keep in mind. The transparency, it has to be more than 70% transparent so that you can see what is outside. And second thing is that any distortion should not be there. Suppose generally this kind of glass is being used in a car. So the distortion is optical distortion. So if you put a bulletproof glass and if you see that by one person is walking around 10 feet away, but the glass, due to distortion in glass, it is showing 20 feet away, so you will always have an accident. So the distortion has to be less and it has to be transparent. So these are being made basically with the glass layer and some inter layer of PVB, polycarbonate, and polyurethane, which are transparent. So these are, the surface are being cleaned. Then stacking process has been done. How many stacking layer you want? 1, 2, 3, 4, like that. Stacking layer is being made. Then some de-airing process is also done, so that no entrapped moisture or air should be there. Because the moment entrapped air or moisture should be there, it will give rise to a defect point or the crack initiation point in the material. Okay, so then autoclave bonding is there. We subject to some temperature and pressure, and that time it will stack to each other and it will make a bulletproof glass. So this is how, from one's concept, the people didn't have an idea before pins to part stop that glass also have sufficient strength which can restrict the bullet movement and can. So people have ideas. Another point is the glass fiber. Glass fiber, you know, all our furnaces or heating equipment where we know we need a temperature, uniform temperature zone. We need to restrict the temperature gradient. We need an insulator. So glass fiber is a good example, or good example of a best insulator. Is a great electrical insulator, and it is a chemical resistant and great fire and heat resistance, and it is also high tensile strength. Not only this is used in furnace, people use as a reinforcement material for the any composite material. Okay, now as I mentioned about this kind of advanced alloy, just give rise to some 2-3 example of composite. Although it's a vast, I'll just give a 2-3 example of composite where it is being used and how it is changing our advancement in today's world. So this is a clear distinction between alloys and composite. You remember one thing: in case of a alloy, a metallic system, mix of 2 or more elements, which is created single phase or multiple material. But in case of composite, you have a 2 or more distinct materials, which is one is matrix, one is reinforcement, such a way that they remain separate at micron level. So if you take in a microscopic scale, so the matrix and reinforcement are different. But in case of an alloy, they are completely visible. You cannot, in a microscopic level, you cannot differentiate what is your matrix, what is your reinforcement. Everybody mix together and make a alloys. Okay, there's some example that application is there. This is a example of you see the carbon composite which has been used as a layer of a rocket nozzles. You can see all the rockets like PSLV, JSLV rocket, they have this exhaust cone. The exhaust cone, the temperature it can reach around, temperature can be reached up to 3000 to 3400 degrees centigrade. Okay, no metallic system can reach that kind of temperature. You need a application of composites here, carbon composites. The carbon composite has been layered. It is used in the nozzles, exit port, throat insert, and thermal protection system, so that we have a successful launch vehicle operation in space. Okay. Not only that thing, inside you see it is a 3000 to 3400 degrees centigrade. Outside that cone is around 250 to 700 degrees centigrade. So that temperature gradient also has to be maintained so that the other operation runs very smoothly. So these are the beautiful example of a carbon composite that are being used in our space shuttle. And another bottom hand side, you can see the figure. This is a small experiment. I'll just give you one example. This is a melting. This is a glowing part. You can think glowing part is a stainless steel which is being melted, and the circular part is a is a um, it's a ceramic composite which is made up of a silica and boron nitride composite is there. You can see the steel is being melted, but it retains its original shape. You can understand how much temperature withstand capability of this composite can be there. Okay. And another example is that some metal matrix composite, copper based metal matrix composite. You have seen the aircrafts. The aircraft braking system works on the brake pad discs. Similar the brake pad discs we have in our car, in our bike, but in fighter aircraft or the commercial aircraft, these are the advanced version of the brake pad. So, which is made up of a steel copper coated steel plate. This plate, and onto that plate we add copper, iron, and silicon graphite. These are the powder, lead powder, which is being hot pressed in a reduction atmosphere to make this layer, because so that you get sufficient friction to stop the high speed train, high speed fighter aircraft. But during operation, when a aircraft apply the brake, you can see that in the periphery the temperature can goes right to 900 centigrade. 900 centigrade. So that much temperature withstand capability has to be there. Okay, and this is the braking operation. So these are the brake pads which are being layered 1, 2, 3, 4. So 4 to 5 layer in each wheel is kind of there. So when the brake application is there, so that brake caliper will apply force onto the rotating discs, and you can stop that thing. So this is kind of an example which is made up of a metal matrix composite, and which is being used in our daily life. And but by giving this description, just to let you know that these are the things which are happening in our day-to-day life, and as a academician or as a researcher, we should appreciate this effect, that and we should keep on developing some new techniques so that the performance of this kind of material will become higher day to day. So with this thing, I will stop my presentation here. If you have any question, I'll be happy to answer the question.
Dear participants, you may write any queries.
I think chat box, anything question is there?
Yes, sir, we have some queries in our chat box. Let's go through it.
Okay. Which SMA is used widely in the uses of strength? The strength, whatever you are using, is a nickel titanium alloy. If you have seen any surgery before putting the stent into the operation theater, they will show to the family member that this is the stent we are using. And if you carefully look that stent, it is written that nitinol, written that nickel titanium. Which SMA is used? Nickel titanium alloy. 50/50. One question is there. Then
So one more question is there. Is bulletproof glass completely not breakable or not?
No, actually, that depends on the glass composition. You see, that depends on, suppose a bulletproof glass, some advanced bulletproof glass, which is made up of, suppose, 10 layers or 20 layers. That 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 can restrict the bullet of a bullet which is firing from a sniper, maybe 10 rounds. So when bulletproof glass has been commercially sold, the specification is given that it can withstand 10 bullets or 20 bullets. That kind of specification is given depending on the specification. It is not completely that if you keep on firing 100,000 bullets at certain point, it will reach its threshold value and it will stutter and it will break.
Okay, sir. Any other queries? Okay. If not, let's conclude our first session. Sir,
Okay.
actually introduced. Okay, sir. Dr. Jenna introduced advanced alloys and composites, its importance, significant applications. First started with the wool steel. It is an advanced material of ancient world. It was exciting to know alloy of in ancient India export to Middle East and Europe by India. We are the main exporters. Actually, it's an alloy of iron with a high carbon wool steel. Then he's turned to superalloys. Given a detailed description about the physical, chemical, mechanical property with their chemical combination and significant applications. Then introduced the concept of shape memory alloy, SMA. Introduced the concept, it's a combination of nickel titanium and the copper aluminum manganese combination. He explained with the biomedical application is used in stent and due to its self-phase transformation process. Then comes to aluminum alloys. Sir said it's more precious than aurum gold, and the combination of aluminum, copper, magnesium, manganese, duralumin, its importance. Then introduce the 20 component. Usually we know an alloy, it's a combination of three or more, especially 3, 4, 5 that we heard now, but it's combination of 20 components alloys is also there. Explained its peculiarities. Then comes to glass. Glass, we know it's amorphous material that we turned to Gorilla Glass. It's a combination of alumina and silica L2O3 and SiO2. It improves the scratch resistance, reduces scratch visible, enables improved strength after scratch while we are using in a mobile screen. And also then comes to viscosity reference temperatures of soda, lime, silica glass explained well. We got a realistic impact by seeing the glass making video also, bulletproof glass video also. And our topic was advanced alloys and composite materials. Sir concluded the session with the difference by saying the difference between alloys and composites. Sir, we are very thank you so much for that highly informative and insightful session. Your explanations and perspectives have certainly enriched our understanding and given us a deeper appreciation of the topic. Thank you very much, sir.
Thank you very much, madam. Thank you.
Thank you, sir. Okay, dear participants, our feedback form link is available in our WhatsApp group and in our Zoom meet. Kindly do your attendance there and fill the attendance, fill the link. Now moving on to our second session for the evening. It's my pleasure to introduce Dr. TPD Rajan. Dr. Rajan currently serves as Chief Scientist at the Material Science and Technology Division CSIR NIST, Trivandrum. Over his long career at NIST, he was progressed through roles including scientist, senior scientist, principal scientist, senior principal scientist, and now chief scientist. His areas of specialization include composite materials and metal matrix composites, functionally graded materials, light alloys, nanomaterials, surface uh, engineering and metal casting, advanced material processing, composite fabrication techniques with a lens towards application in engineering, structural and functional materials. He has also guided several students, multiple PhD theses and master dissertations under his supervision. Over the years, Dr. Rajan has received several honors and awards, including INAE Innovation Potential Award for Best Doctoral Thesis in Engineering at All India level. Then Chandra Menon Memorial Award for Applied Research and Innovative Technology, IAF Industry Foundry Research Award, IIM National Metallurgy Award. He is also active in professional societies, life member of the Indian Institute of Metals, Materials Research Society of India, etc. Additionally, he serves as chairman of the Trivandrum chapter of the Indian Institute of Metals. We are truly privileged to have you with us today, sir. I warmly invite Dr. Rajan, sir, to deliver the second session of this day. Sir, stage is yours. I think sir is trying to join with us. Within a few minutes, he will join with us. Okay, thanks.
So thank you very much, madam. You can hear my voice?
Yeah.
Okay. Thank you very much for the brief introduction. And good evening to all. I'm extremely grateful to Vidya Academy of Technology for inviting me to this lecture. I will share my slide. Madam, you can see the slides?
Yes, sir, we can.
Okay. So very good evening to all. So I think there is a mistake in the title which you had shown there. So the title is on prospects and processing of rare earth added alloys and products. So I think some issue with the slide. I will share again. Okay.
Okay, sir, no problem.
Now it's clear, no?
Clear now, sir?
You can see the slides.
Yeah.
Okay. Okay. Thank you. Sorry for the initial hitches. And prospects. My talk is on prospects of and processing of rare earth alloys and composites. And I am extremely grateful to the Vidya Academy of Science and Technology for inviting me to deliver this lecture on the AICT ATAL sponsored faculty development program on advanced materials, rare earths, and critical minerals. Since rare earth is one of the topic, I thought I will just briefly discuss you on this topic. So before going to my talk, I will just briefly explain about the Council of Scientific and Industrial Research. I think many of the faculties and students, those who are participating, I think mostly the faculties will be useful to collaborate with CSIR because CSIR as a whole and get connected to various institutes so that you will utilize those R&D facilities and the collaborations for the mutual benefit. And CSIR is India's largest industrial R&D organization, which is headed by the president of CSIR is the Prime Minister, and the Vice President is Minister Jitendra Singh, Science and Technology, and Dr. N. Kaleshwari Madam is the Director General. And we have 37 national labs throughout India and more than 3,500 scientists. And the CSIR NIST in Trivandrum is the southernmost lab, which is working on different aspects of materials, chemicals, and all. Like the coming slides, I will explain. And nearby we have a Central Electrochemical Research Institute at Karikudi, Structural Engineering Research Center at Chennai, which is mostly dealing with the civil engineering structures and so on. Then we have CLRA, National Aerospace Lab, National Chemical Lab. I think for more details, you can click on the CSIR websites and see what are the activities going on. Specifically to NIST, we are working in the areas of agro-processing, microbial processes, chemical science and technology, material science and technology, environmental science, Center for Sustainable Energy Technologies, and artificial intelligence and machine learning. And myself and the previous speaker, Dr. Jana, belongs to the material science and technology divisions, and we both were working in the areas of alloys and composites. And to briefly introduce about the lightweight materials what we work. So we are working in the area of light metals, especially aluminum and magnesium alloys, metal matrix composites, casting simulation, near net shape processing, surface engineering, and product development for various applications, especially in the areas of automotive, aerospace, defense, foundry, energy, and biomedical technologies. And rare earth added light alloys is one of our main areas of research. And I think I will just give to the emphasize the importance of rare earths and give the various R&D activities what we are carrying out at CSIR NIST on the areas of rare earth added aluminum alloys and composites. To highlight the different products which were developed are the aluminum SiC first gear housings, which needs a high wear resistance and better stiffness. This is developed for Central Vehicle Research Development Establishment, and it is used in the combat vehicle battle tanks. Then we also collaborate with automobile industries to make aluminum alloy crankcase, aluminum functionally graded cylinder liners, aluminum functionally graded brake rotor disc. And many of these alloys contain rare addition to enhance its precipitation behavior, to enhance its grain refinement, and also to improve the mechanical properties. And we also collaborate with ISRO on developing different types of aluminum alloys, especially for their engine mounting frames, other components. I think in the coming slides, I will explain more on the R&D activities. And we also work with, against with CVRD on the development of piston mounting brackets for Hindustan Aeronautics Limited, especially for helicopter applications. And we also developed a casting software and had license of more than 200 licenses of TRL9, which is called Virtual Casting and AutoCast 11 software jointly with IIT Bombay and 3D Foundry Tech. Coming to the specific alloys which are developed for aerospace applications are premium quality aluminum alloys, especially aluminum 7 silicon 0.35 magnesium alloys, which is used both in the elbow inlets of PSLV, mounting frames of GSLV, and different for our launch vehicles. And especially all these components of elbow inlets are being used. Suppose you have a PSLV or GSLV rocket launch. In all the cases, we use this component which is developed by us. What NIST has done is that we had indigenized the alloy, then made those components and optimized all the process parameters to the required quality, and then the process is transferred to Hindustan Aeronautics Limited, and currently they manufacture all these components and supply to ISRO. And we had been working with the defense organization for developing the thermal management component for which is aluminum SiC composites. So this aluminum SiC composite are being used in the light combat aircraft where they have a digital flight control computer systems. And this digital flight control computer systems will control the whole flight, especially communication with the ground, controlling the whole operation of the flight, detecting the enemy sites for bombing or detecting the enemy missiles, and all the operations happens through the processors which is kept inside this digital flight control computer systems. And normally this DFFC has different printed circuit boards, and these are all mounted on this thermal management plates. And the requirement is to have a high thermal conductivity and low coefficient of thermal expansion. And normally we have copper, which is a higher dense material, and we have aluminum alloy, which is also pure aluminum, which is having a high thermal expansion. For example, the CT of a pure aluminum is almost 23 ppm per degree C, whereas if you have a more expanding material, the problem will be the detachment of the solder joints and other problems on the function. So we have to have a low CT with high thermal conductivity. So hence, these type of aluminum SiC plates are being used. And what we have done is that we made these plates through liquid metal infiltration technique. And this is the imported plate, and this is the indigenized plate, and we had completely made and currently being supplied this to defense organizations. And this also can be used in the unmanned air vehicles and other type of applications. And we also work on this automobile materials, especially aluminum alloys and magnesium alloys. And in the case of aluminum alloys, we develop different categories of aluminum alloys with high strength requirement, high thermal conductivity requirement, and also to improve surface properties, we develop the coatings also. And these two components we had shown, and the setup CVS, which is formerly known as SWAPCO, has sponsored a center of excellence, and these components is developed mainly to have high thermal conductivity and high strength as well as lightweight. The density of aluminum is lower, and it can replace the steel, which is almost 3 times the density of the aluminum. And the thing is that once you have a brake systems in an automobile or any of the heavy vehicles, this is control. The braking is controlled by the air brake systems. And in the air brake systems, when there is a discharge air which is coming out of the compressor, has to have a low temperature. And if you have a very high temperature, the problem is the performance of the brake systems will be reduced. The cooling oil systems will get the increase in temperature, and all the performance will be reduced. So we are having even 10 to 15 degree or 20 degree reduction in the discharge temperature from this crankcase or the brake systems, air compressors, then the performance can. So these aluminum alloys are beneficial in enhancing those properties. And we also work on this magnesium alloy, especially even the rare magnesium, rare earth aluminum alloys. And these are being used in the transmission systems of military helicopters. And at CSIR NIST, we work on premium quality magnesium alloy castings by gravity, low pressure, and centrifugal casting techniques, creep-rust and magnesium alloys, magnesium rare added alloys, grain refinement studies using the different rare metals. Especially our Indian Air Force and other people also use this helicopter engine, crankcase and other with the rare added magnesium alloy. And this is magnesium alloy casting facilities we have, and we have a low pressure casting facilities which can also make prototype components, and these are some of the automotive and aircraft components or helicopter components which we made using the low pressure casting facilities at CSA and NIST. So we also collaborate with the DRDL and BrahMos on the development of magnesium alloy wire coil, which is again a rare-earthed magnesium alloy, which is used in the igniter system of the sustainer engine of supersonic cruise missiles. And all the missiles will have almost 4 magnesium coils, which is used in the igniters of the BrahMos. And these are all being developed using specialized magnesium alloys and to a minimum thickness of 2 mm. And finally, and we had almost supplied currently 10 coils, and each BrahMos missiles will have 4, and this development is under test, is in progress, and once it is finalized, then we'll be continuously supplying these coils to BrahMos. And also this magnesium, rare-earthed magnesium alloys are also used for biodegradable implants in the body. You know that there is a stainless steel or you have titanium implants, and normally once you have any fractures in your body, and if the implants are being put inside the body, what happens after a few months or years, then we have to remove all those implants from the body once it is pure. But the advantage of magnesium is that it absorbs in the body. That means it degrades once the function is over. After 6 or 8 months, we can control or design accordingly. Then it is also not much harmful, because the daily allowable dosage of magnesium in the body is almost 350 grams, and this is absorbed into the body, and once it gradually degrades. And the magnesium zinc gadolinium is one of the rare earths which is very widely used, and we also do the coatings, lanthanum phosphates, cerium phosphates, cerium and lanthanum, which are all rare metals, to control this degradation. So we have to have a degradation, but it must not degrade very quickly. So this is one of the very promising material for the bio implants, the biodegradable magnesium alloys, as well as the lanthanum or cerium based phosphate coatings, which is used to control the degradations. And coming to the introduction on the why rare earth is very much important on this aluminum alloys or rare earth. The reason is when rare metals are added into the aluminum, it leads to the refinement of the grain structures. So that means we have the microstructural grains inside the alloys, and these grains get refined by the addition of this lanthanum, cerium, or even the scandium metals, because of the heterogeneous nucleation behavior. And once you have a refined grain structure, this will increase the hardness, because you have more number of grains and interfaces. This will have restrict the movement of the dislocations once you have a deformation, whether you have an indentation or when you apply a load. So this will increase the hardness, and thereby once the hardness is increased, the resistance to wear and fatigue is also getting increased. That means you can make component with better wear and fatigue resistance. And when you make the cast components, it also improves the castability by increasing the fluidity of the metal. And because of the formation of high temperature stable phases, I think in the coming slides I will tell AL11C or the AL3SI, SC. These type of phases have more stability in the alloy, so that your alloy usage can be used. So that means elevated temperature, and also the forming of the stable high melting compounds. And these cerium or scandium will also have improved corrosion resistance of the aluminum alloys. Then you have the butyric silicon modifiers, which also enhance the strength. So what are the applications of these rare earth aluminum alloys? Is this rare because of all these advantages and the properties which is getting improved on the material. So the advantage is that these alloys are being used, especially the rare earth alloys are being used in the aerospace and defense, especially the lightweight, high-strength aluminum alloys with improved thermal stability, which is ideal for aerospace structures and components in automotive, because all the places we want lightweight components to improve the performance, improve the payload capacity. So when the automotive industry is also lightweight engine components reduces the fuel consumption and the emissions with withstanding high thermal loads. And especially in the power transmission, the rare earth alloys are used for lightweight and corrosion resistant cable. You know that all the electrical conducting cables which you see in front of your house or industries or the institutions all are made of aluminum, and these aluminum have very minor quantity of rare earths, because these rare earth will improve the corrosion resistance of the cables, and also it provide improve the electrical conductivity, and similarly the creep resistance is also improved so that it lasts for long. Even though copper is having high electrical conductivity, the electrical conductivity of aluminum is almost 63% of that of copper, but because of the high corrosion resistance when compared to the copper and the lower density, the aluminum and the cost effectiveness, aluminum is very widely used, and especially the rare earth aluminum is very widely used in the the energy sector, and is also used in the wind turbines and solar panels as structural materials. In the case of electronic devices, we know that high conductivity and wear resistance alloys, wear resistance alloys for connectors, heat sinks, and casings in electronic equipments, even mobiles, laptops are all made of either rare earth aluminum or magnesium alloys. And even the rare earth containing aluminum powders are being used in the 3D printed components to improve the mechanical properties. And in the case of major restrictions of common commercial aluminum alloys are the low melting point of the phases which is present in this material, and lower hardness, that is because aluminum is relatively a soft materials, and once you have the high thermally stable phases just like the AL3 SC precipitate phase, which can mitigate the hard cracking by modifying the phase morphology, or the phases just like highly thermal stable AL11 CE3 or AL11 LA3 phases. These phases are very stable and it provides enhanced high temperature strength when compared to that of the traditional alloys. And we have a lot of rare earth which is being seen, especially cerium. And neodymium is one of the other rare earth which is being used to make neodymium iron magnets. Then we have gadolinium, erbium, ytterbium, lanthanum, europium, terbium, hafnium, and many materials are there, which is in the series of rare earths. And when compared to that abundance in the earth crust, the very much available is the oxygen and silicon, and then next comes the aluminum. So these are the most abundant elements: sodium, calcium, iron. Then comes the carbon, magnesium, phosphorus, sulfur, and so on. And when compared to all these materials, these rare metals are very much low. Even further, we have this iridium, osmium, and all is also very much rare. And these materials have high oxidation oxide stability, and normally if you want to make master alloys, then normally we use metal-dripping. What we does is that we melt the aluminum and we add some amount of magnesium, and this magnesium will reduce the cerium oxide or lanthanum oxide, and then this will lead to the formation of the spinel, magnesium aluminum spinel, and the cerium is getting dispersed. So we will end up with a master alloy of aluminum and cerium. So in this way, and this cerium, if you see, added to aluminum alloys. So, for example, you take a pure aluminum, the strength of pure aluminum is around 60 to 70 megapascal. But when you add this type of cerium into that, the tensile property is getting increased. So, to a higher extent. For example, 10 cerium has 152 and 12 cerium has 163 and so on. And similarly, the yield strength is also getting increased and the percentage. But normally the percentage elongation will come down. So this is a major advantage. Similarly, you can see that there are various types of aluminum, 12 cerium, and 4 alloys, which shows the higher tensile properties when compared to that of the pure aluminum silicon cerium alloy. So that's so addition of cerium, because of the present the formation of the A11CE phases, it shows very high strength. And again, here also we can see that when compared to that of pure aluminum or other alloys, the cerium containing alloys have very high strength because of the present formation of the high the thermally stable or the higher hardness phases. And these are the phases which normally get formed inside the aluminum 12 silicon alloy. And these phases will impart the enhancement in the properties. And these cerium added alloys are being used to make storage tanks and also the aviation cylinder heads and many other air cooled cylinder heads for even automobiles and so on. And even the rotary engine rotor cases are being made by aluminum 8 silicon 10 magnesium alloys. And similarly, the 8 silicon 10 magnesium alloys are also being used to make automotive cylinder heads and various other components because of its high temperature and high thermally stable phases. And we can see here, I think it's also, this table also shows that the addition of cerium enhances the tensile properties. For example, if we have an aluminum iron alloy, the addition of cerium keeps on enhancing the ultimate tensile strength from 490 to maybe around 570, 610, and so on. So that means addition of cerium always enhances the tensile properties in many of the cases. But after a particular percentage, the problem is it forms, get coarsened and the properties get changed. Similarly, you take the another element, which is the lanthanum. The lanthanum addition also, very minute quantities of 0.05, 0.1, 0.2, 0.4 or 0.6, you can see that the increase in the lanthanum content enhances the mechanical properties through the reduction in the secondary dendritic arm spacing. That means it reduces the grain size. So this grain size will enhance the mechanical properties. For example, if you see increase the lanthanum content, the mechanical properties, especially the UTS, is getting increased up to 0.5 percentage. After 0.5 percentage, 0.1 percentage, sometimes what happens, there is a coarsening of the precipitates. So that leads to the detail. So we have to optimize the usage of this lanthanum phases into the alloy, and there has to be an optimum volume fraction of the alloys has to be used. Again, this is also how the addition of the lanthanum in aluminum alloys, especially aluminum 7,4 copper alloys, how the grain structure is getting refined. So these are all holes, alpha phase, which is getting refined by the addition of the aluminum, the lanthanum into the aluminum alloys, especially the very finer quantity. So this shows the reduction in the aluminum grain size with very minor percentage. There is around 0.5 percentage, shows almost 443 micrometers. And in the case of with skews cast or the application of pressure, we can see that it's almost 204. So the combination of the addition of the lanthanum with the application of skews pressure up to 775 megapascal, it shows a reduction of the grain size. So this reduction in the grain size again enhances the mechanical properties of the alloys. Here we can see that the mechanical properties of the alloys is getting increased to 274 when compared to the other alloys with 0.3 percentage of the main lanthanum addition. And these are all, so we will see how the cerium mask alloys are being prepared. So normally what we have to have is that you have to take pure aluminum, magnesium mask alloy, mix it to that, melt it. Then we have to add the cerium oxide in a very low content, then mix it with stirrers by stir casting. Then after some time, this cerium will get dissolved into this and the spinels will get formed. And the spinels can be removed from the top along with the oxides, and the cerium will get dispersed. So we can either make aluminum cerium mask alloy or aluminum lanthanum mask alloy, or mixture of aluminum cerium and mask alloys for these applications. And we also evaluated this aluminum cerium masterlife precipitates, and we found that mostly it is of alpha aluminum primary phase and Al11 cerium phase or Al11 lanthanum phase. So this can be detected by the XRD techniques. So these rare earths of cerium or lanthanum, which is formed, and again this master alloys will be added to the other standard alloys as a grain refiner or eutectic silicon modifiers. So this again shows formation of the aluminum 11 cerium precipitates. So these are the precipitates which the optical microstructural evaluation shows, and the SCM micrographs also shows very fine precipitates of aluminum cerium in the alloy. So this shows scanning electron microscope with the dot mapping of the EDX, and which shows a very fine percentage of cerium. Again, in the case of lanthanum also, the final precipitates which is dispersed along with this. So you can see these are all present in the grain boundaries. So these are the precipitates of lanthanum, and we can clearly see here also in the microstructures. Again, this similar structure with EDX mapping. And the DTA studies also has shown the formation of this aluminum cerium phases. Especially, we can see that after higher percentage of cerium, so it forms this aluminum 11 cerium 3 phases, which is eutectic phase, which is normally used as a grain refiner in the aluminum alloys. These are all about the enhancement in the properties of A3 phases cast alloys by addition of a minor amount of cerium, which increases the hardness as well as the mechanical properties by the reduction in the grain size. And again, we had done the studies on the cerium addition into the mechanical properties of different alloys, ADC3M and with ADC3M with 0.02% cerium with heat treatment, which shows enhancement. Similarly, this is a A356 alloy. This is again with LM30 alloy, which is a very high silicon alloy. So all the silicon alloy shows very high strength when compared to that of the base alloys. So the next system is aluminum magnesium scandium alloy. So the advantages of aluminum magnesium scandium alloy is this scandium forms very fine precipitates of Al3SC, and this Al3 is a highly thermally stable precipitates which enhances the properties of aluminum. So normally this aluminum magnesium scandium alloy is having very low density, and it's having very good weldability. When you have a common aluminum alloys welded, the strength will be around 180 to 80 MPa. But this alloys will have even the weld strength of 230 to 280 MPa. That means structures will have better properties. And it has excellent damage tolerance, good corrosion resistance, deep formability, thermally stable, and easy to recycle. So currently they use this aluminum copper-based alloy, which is highly denser alloy, and going for this aluminum magnesium scandium alloys, which is a rare earth scandium added alloys. So the advantage is that straight away it reduces the density almost 4 to 5%, and the strength is also getting increased. So aluminum magnesium scandium alloy, which is currently imported, is being indigenously developed, and we have transferred this technology of making the alloys into rolled sheets to an Indian industry, and the industrial trial is being currently going on. And if you see the literature, we can see that a lot of studies on the impact of scandium on different aluminum alloys have been studied. Either it's 171 or even 1 on 23, or even the 5000 series and all. And just to some of here we can see that for example, aluminum 2 magnesium 0.5 scandium, 4 magnesium, 6 magnesium, even 4. So here we can see that the strength is getting increased by the addition of scandium jointly with that of the magnesium alloy additions. So the yield strength and the UTS is setting. For example, the 4 magnesium with 1% scandium shows very high strength. So that means this strength is observed by increasing the cold rolling, 83% of reduction in the cold rolling and the age conditions. So this particular alloys, as I mentioned in the previous slide, is being used can be used in the aircrafts for lightweight as well as high strength applications. And what happens when the scandium is added to? So this is a normal microstructure of an aluminum copper lithium alloy. And once we add the scandium, so the A structure is without 0% scandium, and the B is 0.12% scandium, 0.16 and 0.32% scandium. So you can very clearly see that the grain size is getting reduced. So one of the way to enhance the strengthening is by reducing the grain size. I think you remember in the first slides which I mentioned. Finer the grain size, enhance the properties. So when we had measured the average grain size, so the average grain size in the as cast alloys of aluminum, copper, lithium, without any scandium is 216, and gradually it reduces to 98.1, 0.16, and 0.3 percentage scandium. So you can see that very clearly. There is a reduction in the size, that is size of the alpha aluminum when we keep on adding the scandium into the because of this, these properties are of the alloys is getting enhanced, is getting formed. And once you don't have this precipitates, normally it will be very coarse structure. And once we have very finely dispersed precipitates, the microstructure get refined. As well as what happens is that when there is a dislocation, when you have an indentation or when you pull it apart by tensile loading, these precipitates will not allow the dislocation to happen or to have very faster dislocation and deformation. This arrests the dislocation so that this enhances the strength. These precipitates enhances the tensile properties of the material, the hardness of the materials and so. So we had during our initial studies, we had done a lot of optimizations by using the gravity cast plates, fuse cast plates, and the addition of the scandium into that, and how the properties are getting increased. So we found that the gravity cast plates and the fuse cast shows almost 248, 240 megapascal, but the fuse cast shows very high percentage of elongation. And a detailed microstructure also shows the AL3 SC ZR. Once you have a zirconium phase along with this, it again enhances the mechanical properties. I think I'll go in the details of the processing. A lot of alloying additions are being made to make this material, and this is a fuse cast plate. This is a fuse cast plate which we have made. That's AA5028 fuse cast plate. And these are the precipitates of aluminum 3 SC scandium, which normally strengthens the aluminum alloy. And again, these are the detailed microstructures of these alloys. This is before as cast and after homogenization. So after homogenization, we can see the formation of this very fine precipitates. And again, these are the studies on the fuse casting, that is gravity and fuse cast. So fuse casting means normally we apply the pressure and do the and here we can see that as cast has 116 yield strength and 226 ultimate tensile strength. But we homogenize and do the T6 heat treatment, it enhances to 283 megapascal. So heat treatment also has a major role in enhancing the properties. So these particular alloys are being made, and we had now transferred it to an Indian industry roll sheets. So I will just briefly tell upon maybe another 15 minutes on the metal matrix composites, where also we have this matrices, rare earth matrices. And MMCs offer high specific strength modulus, replacing heavier parts. And metal matrix composite provides high adhesive and wear resistance, high abrasive resistance, good thermal conductivity, controlled thermal expansion, and good damping properties when compared to that of normal alloys. And the commonly used magnesium alloys are aluminum, copper, magnesium, zinc, and steel alloys. And initially, the composites which is developed is based on boron, carbon, silicon carbide, fiber reinforced alloys, and so composites. And these composites were the uniformly are the continuously dispersed fibers, source, unidirectional and bidirectional, multidirectional layouts and properties. And the fibers which is used are higher in cost, and it provides anisotropic properties. And however, the fabrication routes are very much limited, and the applications are very limited to defense and aerospace structures. Then they started introducing the discontinuous phases, just like short fibers and viscous and particulates are of ceramic reinforcement. And these are very cheaper reinforcements, and the cost-effective methods, fabrication methods are being implemented, and large-scale production and the commercialization of these discontinuous reinforced composites has happened. And these are discontinuous reinforced composites provide highly isotropic properties, and these are being used in both aerospace, automotive, and general engineering applications. And to manufacture these MMCs, we have solidification processing routes, especially the liquid metal casting, semi-solid, spray casting, infiltration, and in situ processing techniques. And solid state, we have powder metallurgy, diffusion bonding, pultrusion, and all. So I will just only consider the solidification processing routes, because solidification processing routes use this alloys in molten conditions, where normally they add this type of rare metals into the matrix alloys to enhance the properties by the grain refinement, as well as to improve the wettability and so on. And the first technique is the liquid metal processing technique, where we have this the aluminium, the alloys which is taken, the ingot is kept in the resident heating furnace, and it is melted. And once the metal becomes molten, the surface treated reinforcement are added into the metal, and the required alloying elements additions or the elements which is required to increase the strength or the wettability or the grain reference, all are added. Then it's mixed. Then the components are cast components or the billets, or it can be directly cast into the required components using the specially skews cast or pressure die casting techniques. The rolling, extrusion, and forging techniques are also applied on the billets or the plates to make the structures. Or even we can remelt these billets and plates to make the components. So the advantages of liquid metal processing routes is easy adaptability with conventional melting and casting techniques, direct component making, large-scale production, and controlling the dispersion of the reinforcement and the casting defects. Interfacial reaction is less in the case of, it's a problem, but it can be controlled by having some coatings, and the reinforced surface treatments are normally required. And another disadvantage is that reinforcement size is limited to 10 to 100 micrometers because of the difficulty in the dispersibility. So a large difference in the density between the matrix and the reinforcement also will create a problem. So these are the components which I had shown earlier in the initial slides, which are made by the liquid metal stress casting. There is aluminum 356 15 SiC components, and these are the gear housings and the piston ring components, which has lightweight, high wear resistance, and high strength. And this composite melt is made, then we are pouring into a sand mold, and this is how the initial raw castings look like. Then we remove all those risers, runners, and then we machine it to this particular shapes. And these are all being used in the amphibious battle tanks. So currently it's under development. And another is the boron carbide, because boron carbide is one of the well-known reinforcement which is used in the neutron shielding application. That is, introduction of the boron carbide reinforced composites into the aluminum matrix, which enhances the neutron shielding application. Because if you have a spent nuclear fuel or the nuclear fuel which is taken from the processing plant to the nuclear sites, normally it will have a radioactivity, and normally it is carried through the common road. So all the structures and the containers will have either lead or the boron based material because this radioactive neutrons are absorbed by this boron. So normally this boron carbide is dispersed in this metal, and we can make this boron carbide reinforced aluminum composites for neutron shielding applications. And another one is that copper coated boron carbide is made because normally the wettability of the boron carbide into the aluminum is very difficult. So we normally coat this reinforcement with the copper, and this is the copper coated boron. Then we'll be dispersing it so that the wettability is being improved to uh, disperse it. And another application of the aluminum composite is that we can make this aluminum SiC composites as for the armor application, especially for the defense. Here two things are there. One is either we can make the metal with dispersion of SiC, which normally when you have a bullet hit, presence of SiC particle will absorb the energy and it. And another category is that we can have a porous preform, and once the porous preform is there, this preform can be infiltrated with the liquid metal, and we can make a functionally graded armor. So if you have a one end with the high silicon content and the other end with liquid pure metal or the pure alloy, then what happens once the bullet hits this high silicon content area, it absorbs by fracture mechanisms, and then this by deformation mechanisms, the whole is getting arrested. So this is a functional graded armor material which are developed for defense. So there is another technique called semi-solid processing technique, which is where we will not completely melting the metal to liquid, but we normally disperse melt the metal to a particular semi-solid region, so that what happens is that this partially melt content will be always have alpha phase, and because of the presence of the alpha aluminum, so this dispersion of the very fine phases is possible. So the advantage of this semi-solid processing is having high integrity near-net shape components, more dispersion or the uniform dispersion of the particle happens, minimum interfacial reactions, and large-scale protection of the component is possible. So the next technique is called the liquid metal infiltration processing. So this manufacturing process involved the making of a porous preform. So that means we have to have a porous preform which is preheated and kept in the die, and then what we pour the metal over this, and application of a ram, the liquid metal infiltrate through the porous body, and it gets the metal gets infiltrated, and the composite is getting formed. Either we can have a pressure by vacuum pressure, or pressure can be applied through the preform, or by vacuum and pressure combination we can make the component. So this is a technique. Normally what happens, there's a skew casting is there. Generally in an alloy process technique, we pour the metal and we apply the pressure, and the shaping of the component is made. But in the case of skew infiltration, we keep a preform here in this die, and that's how the components is getting formed. So skew casting, we have a direct type of different types of skew casting techniques. One is the direct skew casting, where we can apply the pressure directly into the component, or we can apply through a piston, and where you can see that the metal is filled, and there is a feeding system through the pressure is getting applied, and the cast component. So so there is an runners and risers is not required in both the cases, and good yield is made by this skew casting techniques. I think I'm not going to detailed advantage, but a couple of advantages that it can form near net shape components, and fine grain microcell components can be formed using this skew cast. And this skew casting technique is used to manufacture the rare earth added aluminum alloys and other components, as I mentioned in the previous slides. But the limitations is that high initial investment and limited size and shape complexity, and tooling cost is also very high compared to that of the gravity and other casting techniques. But the advantage of the skew casting is that once you apply the pressure, what happens is that in a sand cast you have a very cold structure, and So it is getting refined slighter, but in the case of excuse cast, you can see that it is almost completely getting refined because of the very fast and fine this one. So here we can see that the grain structure is getting refined. Because of that, a sand cast material which is having a typical tensile strength of 226 is getting increased to 347. So that means enormous increase in the properties is there by going for a pressure die cast component. Again, this is a skew casting of the aluminum, silicon, copper, one magnesium which is carried out. And here also we can see that application of the pressure. This is a gravity cast and this is skew cast. Very finer microstructure cast components are formed. So the grain size is almost 22 micrometer and the grain size is here, it's almost 78, and the secondary dendritic arms width. So a secondary dendritic arms width, this is the primary dendritic structure and these are. So the arm spacing between these structures are here we can see. The spacing is 24 here and it is getting reduced in the case of 14.4 in the skew cast structures. So in turn, what happens is that these alloys will have very high strength. The skew cast alloys will have almost 385 megapascal yield strength, but in the normal gravity cast is having around 270. So that's advantages of having. So this is a pilot scale facility which we have at CSIR NIST. So this is a skew casting facility where we have a 100 kg melting capacity, and which we can melt the metal and pour into the feeding system. We have an auto ladder system. It get poured, and this component is getting pressed, and it is commonly getting ejected. And here, this is how the die looks like, and the components is. So once the metal is getting injected, it is similar to that of high pressure die casting, but here the pressure is completely applied on the component and the casting is made. So 1 to 5 kgs of the component, a product size of 800 by 800 and 1.5 mm is made. And here we can use this cold compressor head and heat sinks, and different types of components can be made. And one of the component which we developed is on cold compressor plates, which is used in the high-speed trains and other automotive systems for one of the Belgium company, that's Atlas Copco, which we had developed and transferred to them. And we had also developed this rare earth added, which I had already mentioned, this one for skew cast components. I think this, so this is how the preform is being made. So what we have a silicon carbide powder, then we have a polyethylene glycol, then we have the aluminum powder, we mix it, then we do the green compaction, and after green compaction, we do the sintering. And during sintering, what happens is these PEGs will get burned off and we will end up with a porosity. And then we keep this porous material here, and then we pour the metal and apply the pressure, and this is how it's getting infiltrated. So these are the details of those. So here this is a green body, that is a sintered one. Then after sintering and heating, so even we can, instead of polyethylene glycol, even we can use salt also. What we can do, we can form the salt, melt it, or you can even dissolve it after the sintering, and you will end up with a porous structure like this. So once we pour the metal and apply the pressure, then it gets infiltrated through this fine pores, and you will end up with the cast compound. And this is how it looks like. You can see this is a porous this one, and once we completely infiltrate, we can see the uniform distribution of the silicon carbide particle into the aluminum matrix. And what happens is that if we keep on increasing the percentage of silicon carbide, we can see that the hardness of this material is getting increased. So this concept is used to make the functionally graded armor plates. And also same methodology we had used to make the, I think initial slides I told about the aluminum SiC thermal management component. So here we use this aluminum silicon magnesium alloy with, which is a green variety high thermal conducting magnesium alloys with 50 micrometer of particle size, and reinforcement concentration is almost 68. And we are able to make a uniform distribution of the material with the density is around 2.9, hardness is 186 BHN, in heated condition is 210, then 9.73, the 10 raised to 6 is the actual CT, thermal conductivity 176 The compression strength is 491 and 119 is modulus of this material. So this I think I had shown you earlier. And so you can see the impact of the particle size. So here we had changed the particle size of silicon carbide and we had evaluated the thermal conductivity. And we found that finer the particle size, the thermal conductivity is low. And once we have a higher particle size of 110 micrometer. So that means we change the particles from 10, 20, 50, 75 and 110. So 110 shows high thermal conductivity because in the case of SiC particles, so here we have two materials. One is the aluminum alloy and we have silicon carbide particles. And when the thermal conductivity is by two different mechanisms, so this aluminum alloy, there is a free electron flow. And because of this presence of free electrons, so there is and because of that vibrations, we have this thermal conductivity happens. But in this case of ceramics, there is phonons. The phonons are there, and these phonons conduct the materials. These are our quantized particles, and which normally because of the vibrations, the thermal conduction take place. So there are two different types of mechanisms which is there, and because of the higher thermal conductivity of this SiC particles and the presence of silicon carbide, it enhances thermal conductivity. Also, because what happens is that we have very fine particles, the interfaces are more, and there's a scattering of the conductivity. But in this case, there is a photon scattering or there's no continuous flow. But once you have a larger particle, the inhibition is very less, so that you have a high thermal conductivity, or even if you have it is used in the thermal management plates also, then you can have a high thermal conductivity management plates. So we had seen the silicon carbide, but if you use graphite, it is infiltrated, then graphite will have very high thermal. But the problem is graphite in this direction shows very high conductivity, and other direction. So that means this direction has high thermal conductivity, and if you come from top to bottom, the conductivity is very less. So here means this is the direction because of these particles are aligned. Graphite is a two-layered structure, and normally this layer has high thermal conductivity, and because there is a spacing separation, the conductivity is very less. So you can see that the annealed area shows annealed one, which shows very high, low thermal conductivity in the graphene, the layered structures. Then we thought that we will use diamond, which is again having higher thermal conductivity. So we had taken different types of diamond particles, and we infiltrated in, and this is a component. And here what we had done is this is a metal bonded diamond which I had used. So for this present study, we had taken this 356 alloy, then with synthetic diamond, natural diamond, and metal bonded diamond. And we found that this metal bonded diamond, the interface is very good, and the thermal conduct, and it's a highly crystalline the diamond particles, and which shows very good thermal conductivity. That means you have the alloy is 134, and by infiltration we can see that the thermal conductivity is enhanced up to almost 479 watts per meter Kelvin. And we had also used this carbon fibers to make composites. When the carbon fibers are stacked and infiltrated, we can see that these are stacking of carbon fibers in different directions. So these longitudinal directions, and this the horizontal or the diameter directions, we can see it's completely infiltrated. And this particular composite has very good self-lubricating properties, because you have these fibers, which is a carbon fiber, and because of self-lubrication, you can see this is a pure alloy. It wears off very good. The wear rate is very high. But you have a composite, the wear rate is very less. And this can be used to make your pantographs, which is used in the railway systems, because the carbon fibers and other things has electrical conductivity, and because of the low wear resistance, this can be used in those systems. Again, we have studied with the graphene systems. Graphene also has shown very high thermal conductivity. I think I will just give the sum up of this result. I will go to the details. So these are all the aluminum graphene TEM studies, which shows the bonding is perfect. And I think so. The CT, the coefficient of thermal expansion, is also getting reduced from 21.7 to 10.28. The mechanical properties increased, especially the hardness from 105 BHN to mostly to 125, 130 BHN. This 103 for 356 Li and 130 for this one. That is for the graphene composites. Again, the tensile strength for A356 alloys in the compressive strength is 386, and this is getting increased to almost 496 megapascal, and the tensile strength from 239 to 296 megapascal for by the addition of the 0.5 graphite. And if you are having a higher concentration of the graphene, what happens? The graphene get agglomerated, and this is the region where it gets failed, the microcracks. But if you have a proper dispersion, then it not the you can see the throughout the area it is completely dispersed. And the thermal conductivity is also getting increased. This is at 20 degrees, that's at almost 25 degrees at room temperature. By dispersing and proper dispersion, you can say almost 224 watts per meter Kelvin. The thermal conductivity are able to achieve it. And the wear resistance, again, because of the self-lubrication behavior of this graphene, the wear resistance, this is a wear loss actually. So wear loss of the 356 alloy is higher, but once you add the graphene, this 0.1 percentage, 0.3 percentage, 0.5, and then it's 1.75. It shows that increasing the graphene content because of this presence of the self-lubricated graphene, it is getting increased. And here we can see this. These are the carbon-rich layer, which is found, which is called a mechanically mixed layer, which will not allow further the wear loss. So this will act as a lubrication layer in the composites. So this can be used to make thermal management plates or even the pantographs or any of the things because of the higher thermal and mechanical properties. The overall application of this metal matrix composites, even the rare earth metal matrix composites, are especially in the automotive applications, just like cylinder liners, automotive brake rotor systems, the intake exhaust valves, or the brake components, or the drive shafts, which is having high strength in the automotives, cylinder liners, engine blocks, the brake calipers, again engine blocks for the Honda and the brake drums. This is also the disc brake systems of Vanco, and this is a high-speed brake pad, brake rotor disc, which is used in the high-speed trains. These discs are being placed here, so this will allow the high-speed trains to get stopped. And we also have MMCs in the aircrafts, which is used in the mid-fuselage structures of the space shuttles or in the high-gain antenna waveguides of space Hubble telescopes, and even the joints, and mostly the thermal management application, especially in the electronic packages, then space shuttle orbiter cargo applications, ventral fins, and this in the fighter aircrafts, and even the exist guide vanes in the case of engines. These 6092 SIC composites are being used because of its improved erosion and high wear resistance. Again, this titanium-based MMCs, which is used in the fighter aircrafts. And there's another composite, which is an aluminum laminated composites, which is what we does is that this A380 aircraft, the whole outside structures are mostly made of these glare composites. So these glare composites are almost 0.38 mm thick aluminum sheets, and the glass fiber reinforced resin bonded. These are bonded laminated things, and which is having lightweight and high strength, which is used in the aircrafts. So to summarize my talk, lightweight materials play a critical role in the weight reduction of aerospace and automotive components, and aluminum is very widely used. Aluminum alloys among the transport and energy sectors, and here the importance of rare earth addition into the aluminum alloys, either in the form of lanthanum, cerium, mish metal, or the scandium, is mainly it improves the properties of all the cost and high temperature properties of this composites or the alloys, owing to the refined microstructure, due to heterogeneous nucleation, constitutional supercooling, or the formation of very fine precipitates of aluminum scandium precipitates, or the aluminum cerium precipitates, or aluminum lanthanum precipitates, which overall strengthens the alloys. So the Arbither import substitution self-reliance gives a major thrust in India for the development of rare earth-based lightweight metallic materials. And the currently a strong linkage between the industry and R&D is required to have more innovations in the area. And rare earth alloys is having a lot of potential, and it's you know that there's sanctions from China for exporting this, and a lot of even global politics is there on the, so you can emphasize how much important are these rare based materials. So thank you very much for your patient hearing, and I will stop my share, and if any questions are there, I think you can ask me.
Dear participants, you may ask your queries now.
So I think one of the question is, I can see is name one aluminum alloy which is used in the rockets. So the one aluminum alloy which is used in the rocket is 2129. That is aluminum copper alloys, which is currently used. There are a lot of alloys, as I had shown. No, in my talk itself, I had shown that A356 alloy is used, which is an aluminum magnesium scandium alloy. And apart from that, 2000 series 2129 alloys, 6061, 7175. A lot of aluminum alloys are being used in all the rocket parts. If you take outside structures of these rockets, most of these materials are aluminum alloys, because the main requirement of the aluminum alloys in rockets are the lightweight, high strength, improved weldability, and so on. So mainly to improve the payload, these aluminum alloys are being used. Aluminum, especially the aluminum, copper, silicon, aluminum, copper, magnesium, aluminum, magnesium, silicon, aluminum, magnesium, scandium, all these alloys are being used in one or the other parts. So any other doubts and
Any queries from the participants?
I think on my name on alloy. There is another question is, so what are the major challenges during mixing and homogenization of so mixing, one of the problem is wettability. Wettability between the reinforcement and the matrix is a problem. Then second, if there's wetting is not proper, then what happens is that the particle will not get dispersed. It will come to the top along with the oxides. So normally what we do is that we add this wetting promoters, especially the magnesium is added to the aluminum, or to refine the alloys for homogeneous distribution, we add cerium and other materials, or even we can coat the reinforcement with highly wetting promoting, especially the copper or nickel, to improve the wettability. So sort of the problem is the wettability. Then the problem is if you don't have the proper stirrer, then that is also a major problem. So a design of a proper stirrer, the optimized temperature of dispersion, and the particle size. And if you're using a purely liquid metal, then particle size of 10 to 100 is mine. Above and below is very difficult. And if you want to have a very fine particle, then you can go for a semi-solid dispersion routes. So these are the challenges, and there are ways to solve this also. Is possible. Then I think, sir, please share your email. Okay, my email ID, I think I will put it in this one, and anybody can contact. I think even the introduction slide I had shown it. So chippirajan@gmail.com is my slide, and my phone number also I will give. Anybody want to 944-703-5439 is my phone number. So either if any of the faculty is doing their research, they can collaborate. We have a lot of R&D facilities at CSIR NIST, and anybody want to come here and utilize these facilities, you can collaborate. And any one of your students want to do your projects or your PhD at here, that also is possible. So that also is possible at CSIR NIST. And even the faculties can do their PhDs if they are only with the MTech. or you can send your students for internship and other programs. You can contact me anytime. I think I can give the details. Okay, madam.
Okay, sir. No other queries, I think. If not, let's conclude the session. Actually, Rajan sir started the session with a small introduction of R&D organization CSIR and mentioned the various disciplines in which the sir is getting engaged now. Then passed through lightweight metallic materials, aluminum alloy components for space applications, lightweight low CT and high thermal conducting aluminum MMC for thermal management and avionics system for fighter aircraft system. So said the CSIR is the Center of Excellence in the sense an interdisciplinary technology development center with a focus on lightweight metallic materials and components for automotive application. Then sir gathered the lightweight magnesium alloys gathered attention in scientific world due to the several peculiar and unique properties of magnesium. Then the defense system also is used as the development of sustained engine of supersonic cruise missiles. And sir explained the application in biomedical application because it is a positive host response for bone growth. Even we know magnesium is an essential mineral for human body. It has so many applications in biomedical and biodegradable implantation like that. Then sir mentioned why rare earth metals are important in various applications such as aerospace and defense, automotive industry, energy sector, electric devices, additive manufacturing, etc. Sir explained all the things very well. By Ellingham diagram, thermodynamics aspect of the metal aluminum is explained very well. Then passed through the schematic diagram of processing of aluminum cerium master alloyed using Sevio oxide. Then the characterization studies such as X-ray diffraction method and SEM EDS analysis, we can see the presence of extra metals on the surface through SEM images very well. Then the role of cerium in mechanical and thermal properties explained very well by very clear graphical representation. Then went through the MMC manufacturing technology, solidification processing and solid state processing by a flowchart diagram. Aluminium composite armors for defense applications are very well explained. Sir covered the areas such as aluminium diamond composite for thermal conductivity applications with interesting fact and very clear SEM images. Then some mentioned the graphenes as a self-lubricant behavior by showing the proper solid evidence with the explained well, and summarize the topic with the with the future scope of lightweight material, aluminum alloys, rare earth metals. Also mentioned the collaborative scope with the industry. Sir, thank you very much, sir, for sharing your valuable knowledge and experience with us. Your session has been truly enlightening and beneficial for all the participants. Thank you once again, sir.
Okay, thank you all for your patient hearing, and I'm extremely grateful for the Institute for inviting me, and best wishes to all the participants. And if any help or information, they can contact anytime. Thank you all. Thank you very much.
Thank you, sir. Thank you for your wholehearted support.
Okay. So I can leave now,
Dear
madam.
participants.
Yeah.
Okay, sir. You can.
Okay, thank you.
Thank you, sir.
Thank you.
So, dear participants, this is a kind reminder. Please submit the feedback forms for the 2 sessions separately of today's program. Your feedback is very valuable and will help us to improve the quality of future sessions. Also, both feedback forms is essential for recording and updating your attendance. Then, with this, we come to the conclusion of day 2 of our ATAL FDP. On behalf of the organizing committee, I extend my heartfelt thanks to both our esteemed speakers for dedicating their time and expertise. I also thank all the participants for joining us this evening with a great enthusiasm. We look forward to meeting you again tomorrow for day 3 of the program. Thank you and stay safe.